Let's take a look at this example. The given function models the displacement of an object moving in simple harmonic motion. So this is a simple harmonic motion problem. We need to find the amplitude, the period, the frequency, the phase shift, and the least positive value of t for which d equals 0. Now, when we find the least positive value of t for which d equals 0, what we're essentially finding is the least amount of time that it takes for this thing, whatever it is, whatever movement we're mimicking here, whatever movement we're modeling here, is the smallest amount of time that it takes to be in equilibrium. So we're finding the first place at which this thing is at equilibrium. But let's start by finding the amplitude. We know that the amplitude is the absolute value of a, and a is just the coefficient of the trigonometric function. So there's our a, which is 1/4, and the absolute value of 1/4 is 1/4. So our amplitude is 1/4. And remember, what that means is that when we're modeling whatever we're modeling here, the distance from the equilibrium to the peak of a wave is 1/4 unit. And the distance from equilibrium to the bottom or the trough of a wave is 1/4 of a unit. All right, let's find the period now. And remember that the period is 2 pi over b, or in this case, it's 2 pi over omega. Our b, or omega in this case, is the coefficient of the independent variable t. So here, omega is 1/2. So we would have 2 pi over 1/2, which is the same thing as 2 pi times 2, which gives us 4 pi. So the period is 4 pi, which means it's going to take us 4 pi seconds, or whatever our measurement of time is here, to complete one cycle. Now let's find the frequency. Remember, the frequency is just the reciprocal of the period. So if the period is 4 pi, the frequency is 1 over 4 pi. And that essentially means that we'll complete one cycle every 4 pi units. All right, let's find the phase shift. Remember, the phase shift can be found by c over b, but in this case, it would be c over omega. That would give us c is 1, and omega is 1/2. So we would have 1 over 1/2, which is 2. But we have to keep in mind this is a positive 2. And when we're talking about phase shifts or horizontal shifts, a positive 2 phase shift means that the graph of this function would actually move to the left 2 units. So we would signify that phase shift as a negative 2 phase shift. The negative indicates movement to the left. All right, now let's find the smallest value of t that gives us a d that's equal to 0. So to find that t, we're just going to set d equal to 0 and then solve for t. So we'll have the equation 0 equals 1/4 sine of 1/2 t plus 1. First step to solving this is going to be to multiply both sides by 4. Multiplying the left side by 4 gives us 0 because 0 times 4 is still 0. Multiplying the right side by 4 gives us sine of 1/2 t plus 1, because 1/4 times 4 on the right gives us just 1 sine of 1/2 t plus 1. Now we need to find the two angles between 0 and 2 pi that have a sine of 0. Those two angles are 0 and pi. So that means that our angle, 1/2 t plus 1, has to be equal to 0 or pi. Subtracting 1 from both sides to try to isolate t by itself, 0 minus 1 gives us -1, and pi minus 1 gives us pi minus 1. And then on the right, if we subtract 1, we're left with 1/2 t. Now let's multiply both sides of this equation by 2 to get t by itself, which means we'll have to multiply negative 1 by 2, and the pi minus 1 by 2 on the left, and then multiply the 1/2 t by 2 on the right. And when we do that, we get two solutions on the left, negative 2 and 2 pi minus 2. Now this negative 2 and the 2 pi minus 2 are the two times at which we are at equilibrium. But keep in mind, our instructions say to find the least positive value of t, or the least positive time for which d equals 0. Well, if we're looking for a positive time, that means that this negative 2 is automatically disqualified because it is a negative time. So our only qualifying value is 2 pi minus 2. So the first time that we're at equilibrium is at 2 pi minus 2 seconds.